Alan Kay's talk at UCLA 2024, part 2. Hello, I'm Chris Athanas. I'm a KMP developer. Tech Support said they're coming out. They're going to close that up. I'm going to continue on where we left off yesterday with Alan Kay talking about uh, origins of OP, DARPA, ARPA, Xerox Park, and he's in this section here where he's like, "Can there be a science to computing?" It's like the thing I just noticed this quote here: math has to be neat, but it doesn't have to be real, right? It has to be internally consistent for the most part until you see something that's not internally consistent, like divide by zero or something. It doesn't. But it doesn't have to be real, right? This notation doesn't actually exist anywhere except in our imagination. All right, let's keep going.
And the thing about math is it has to be consistent, meaning neat, but it doesn't have to be real.
Right.
And so this thing that John did was not real, but another hero of mine, Steve Russell, the guy who invented space, and then he did something even stronger along the lines of Newton, which is to explain
I don't know what happened.
Important ideas here about what was lying beneath the surface and why it was really useful to think of doing things in a particular way.
Okay.
And the thing about math is it has to be consistent, meaning neat.
Sorry about the
but it doesn't have to be real. And so this thing that John did was not real, but another hero of mine, Steve Russell.
Yeah, run the math to vet the real universe it creates. I mean, that's a program. If I implement it, we'll have a running system. Okay. He did and we did. Okay.
The guy who invented space war was at MIT, and he looked at John's math and he said, that's a program. If I implement it, we'll have a running system. And John McCarthy said, well, he did and we did. And that was the birth of Lisp.
Oh, okay. This is Lisp. All right. List interpreter, so recursive logic system. Okay, let's keep going.
And here's the cool thing about computing. The theory can also be the model and the artifact, and you can make it real.
Yeah, that is true. That is true. You could have a machine that runs the system. If it's logically consistent enough, it can run by those rules because the rules are so simple, and have an A/B choice that you can run a machine on it for sure. Yeah.
But there are a lot of complaints about dealing with pure semantics is too slow, even after a factor of a million or a billion or more of Moore's law. Still seems to be too slow.
Okay.
On the other hand, you can build a special machine for the semantics that don't fit on regular machines.
Yeah.
Because remember, a computer's only there to run programs. So why not make a computer that will run the programs you want to run?
Yeah, of course. Yeah.
And if you try to optimize too early, like buying a computer before that isn't a supercomputer, before you've done your research, you're in trouble.
Yeah.
Because now you're forced to deal with its problems rather than your own.
Right. So he's saying that to do the Alan Kay type of systems, we're going to have an Alan Kay type hardware, because even today he says the systems are too slow to run with these general purpose ones are too slow to run what he's talking about. I don't. Maybe that's true. I don't know. I'm not sure that is true. But he's saying if we have specialized hardware, that he thinks it's possible. I think he might be right.
So this is the kind of process that the ARPA community went through. And this is a fun story, but I want to bring up the fireflies again. You can't replicate what John McCarthy did because the times are different now. But the fireflies in what he did are still there, and they can still tell us what to do.
Right.
Okay. Here's story number 2. 62 years ago, in 1962. This is in the Sage experimental test computer called the TX2. It was one of these computers that was the building.
Yeah.
And right down at the end of one corner was this guy sitting in front of a silicon.
It was tubes. It was tube based. Each little gate, now that's so microscopic you can't even see it with the human eye anymore. They're all visible and right there in front of you.
Scope screen. And what was he doing? Well, here's the light pen. He was grabbing some ink. And
yeah.
Now this display isn't a line drawing display. It just makes a dot. So there's a program making those
oscilloscope,
lines.
basically.
Now he tells Sketchpad to make them all mutually perpendicular, and you just saw it automatically clean up the drawing. This is why it's called Sketchpad, because you can just draw it roughly. He wants to make a hole in this flange. So,
Right, and and the reason why LK keeps bringing this up, there was nothing like this before. It was repurposing a different system. It was made for missile defense, while it was not being used during the day or during the night. He got access to it, special access. Ivan Sutherland got access to it, and he was able to create this piece of software that honestly is a basis of like how we use all the computers. And so we look at it like, okay, what's the big deal? But at the time, we have to remember that it was all like batch programs and missile defense maps, and that was it. It wasn't. It was just tracking in things and tracking out things. This interactive creation and assisted drawing, it was totally blew people's minds. Like it was like, what? We didn't know this was even possible.
so he says here, make these both parallel and perpendicular. And now the constraint is make these lines I'm drawing to be collinear with the guidelines below. So this allows him to quickly draw a dotted line. Now he's going to make the guidelines transparent. We get a hole in the flange. And notice this is the first system to have a clipping window. He's actually drawing on a canvas about 1/3 of a mile on a side, being windowed here. He needs a rivet. So this is the rough shape of a rivet. Draws this because he wants this as a center for an arc for the top of the rivet. And now he says, okay, make all these lines I'm pointing to here, make these mutually perpendicular. And that will force the drawing into something like a rivet. Maybe he doesn't like that shape. Because he didn't constrain the size of the thing. So here's another solution with those starting conditions. But he decides he likes the one he did first. Now here's another cool idea Ivan Sutherland did, which was to have masters and instances.
Right. So this is the first time someone had thought of like an object as opposed to every little piece being drawn individually. They'd have like one masterpiece instead of objects, or a class, and then objects instances of that class. So this is why Alan Kay brings it up, because this was kind of where that idea concept came from.
So this is not the rivet he drew.
Which in retrospect is like, yeah, of course. How else would you do it? But back then it was like, what the hell?
Instance of the rivet he drew. And the rotation and the scaling are done by knobs that he has on the console. Okay, and wants to show you can make more instances and that these instances can be different sizes. And says, whoops, I forgot. I left the crossbar on there. I should make these guys transparent. So he goes to the master drawing and makes them transparent. And lo and behold, all of the instances obey. So he gets rid of the thing. And he says, okay, make that construction I just did into a master. Now I'm going to make instances of the master. Right? Here's instances of the master that he made of the conglomerate. Yeah, okay. So here's a high resolution picture of Ivan at the console, and he's doing something much more complicated, which is to draw in a bridge. And unfortunately, the movie for this has been lost. It's probably somewhere in Ivan's garage, but for fun, a couple of years ago, we
so this is a little bit old. I'm sorry that
you've
seen this before, but let the old man speak.
So
okay?
Here's a simple truss bridge, and we can connect things up. And if we turn gravity on, which is a constraint, you see it's computing all the stresses and the strains on the bridge.
Finite element analysis. Yeah, it made this was super hard to do, but if Mr. Sutherland figured out he could use the computer to do all the hard stuff, all he had to do was build a UI for it, and it was like, holy smokes, what the? And this basically kicked off the CAD computer aided design revolution. One man did this by himself. I mean, it was probably going to happen at some point, but he did it so early, and people were just like blown away.
And it's continuously computing. So if we add in another strut here, guess what? It ripples over the entire bridge if we hang a weight on it.
Yeah, real time, all this stuff was blowing people's minds.
And so the big idea here is it's not just about imitating drafting. It's that we can simulate any kind of computer-aided design drawing that we do or model.
Yeah.
And we get not just CAD, but CAD sim. So this is a huge, huge idea that's still done extremely poorly today for
Agreed.
most people.
Agreed.
So interact. This is Ivan's PhD thesis in 1962, inventing
You know, when they talked about this AI stuff, I was hoping that it would do this kind of stuff. Would create these animations and these tools that we could use to explore stuff. But I haven't seen it. Maybe there's demos of this. I haven't seen it yet. It would be super cool. All I see is just generating text and generating an image, but none of these like an interactive thing like this. That's you could just add it more stuff to it and have it simulate stuff. Like maybe the moon launch to see if it's possible with those materials. Let's keep going.
interactive computer graphics, clipping windowing, pointing iconic IQ, objects, masters, and instances. We call that object. This is really the first object-oriented programming system that I know of. Lots of nice technical things in it. Automatic dynamic simulations from designs.
Right, because the purpose of the system also like gives it this object oriented idea. But I'm not sure if with masters and instances, but the actual language underneath, I'm sure it was just assembly and the assembly language for this particular machine. And he was juicing it for all it was worth. And he does talk about that a little bit, but yeah, it's not the language underneath that he's writing was not an object oriented language. It was just assembly language. But the concepts he was using started to use this vernacular of instances and things like that.
And you programmed it not in the standard programming languages, but you programmed it in terms of goals, in terms of the constraints that you want in Sketchpad.
Right, but that was the program he wrote was to do that one version of that, not all versions of it, and it was a very simplified, straightforward analysis system just to show that it's possible, and to get people to get. Think we went on to do massive software and hardware companies, CAD simulations, flight simulators, all this stuff.
It had 3 problem solvers that would solve problems, as you could see. So I once asked Ivan, how could you do this in 1 year all by yourself? And he said, well, I didn't know it was hard.
Right. Yeah, once you kind of know the computer and how what's possible, eventually someone like him is going to come along and do something like this because it was just the next step over.
Check out the fireflies from this one. Today, think about what the fireflies from this one are. Okay, and also in 1962, we had this guy who was kind of like Moses opening the Red Sea. He's really interested in saving the world and trying to make people better so they can save the world. So his idea in 62 was to have a screen he knew about Sketchpad. He wanted a screen much larger than that. He wanted to hang the light pen from a gimbal.
Okay, or
so
have it in your
you could
hand.
just pull it down to the table and use it like a pencil and not have the blood run out of your hand when you're using it. And there's this problem
Right, because those pens get kind of tiring holding up your thing
which was
to the screen.
Humans are not very good learners from using tools. We have this pink brain. We use tools in a very pink brain kind of way. So like a hammer we can use to hammer a nail into something, but we can break something with a hammer. You can do a lot of things with a hammer, and we kind of get a hammerness into our brain, but we get very little wisdom about tools and hammers in our brain. And
I'll say the AI ChatGPT is kind of like a hammer where we're not really learning 100% what's going on. We're just banging stuff, bam, 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 bam. It's like, okay, well, it's not gonna really. Let's keep going.
We become a hammerer. 100,000 years later, we might decide to use nuclear weapons on a city. That's a way of hammering them into submission.
Correct.
So part of Engelbart's idea was if you're going to augment human intellect, for crying out loud, you must insert education and training. Because what's happened.
Yeah, but education and training from who? This mythical creature that doesn't exist in this society that believes that nuclear weapons could be a good deterrent, and considering the use of them at times. What society are we living in, Kate? Like, I would love a society of Alan Kay. Where is there one like that somewhere we could go hang out? Because then the education and training would make sense because the people in there all have similar ideas. But if from this society with this, no, man, no, we're just gonna end up in the same place. Come on now.
It is that the powerful agencies have gone up in power by factors of millions.
Yes,
and our brains haven't.
That's the bureaucrats take over.
So you want the education to turn parts of our brain this nice bluish cast and perhaps give us a little more wisdom on using our tools. And then we're a little safer using powerful methods and powerful languages and so forth.
We hope.
So this 5-unit thing was.
It's always the intention of the user, right? And it seems like the first thing humans want to do, they get super motivated, is use it as a weapon. Is like the first thing we do with it. And if we can survive that, well, maybe we'll figure out some more stuff that we can do with it.
It's Engelbart's idea of what you really had to do if you're going to do this thing. And you had to do it not just for a person, but people in groups. So the groups have to be organized pretty much the same way. This allows to
I
get
mean,
enormous
from which society, sir? Maybe the 50s and 60s society that made sense, sort of. But you're talking about this society with these set of values? Oh man, there's gotta be groups of people somewhere that are thinking the way Alan Kay is looking, but I haven't heard of them. Not since the Xerox Park days, not since the 80s.
amounts of synergy between the individuals. They can be the different stars on the diagram I just showed you cooperating together.
This is, I guess, it's all online. There's no physical place for this.
And 4 years later, they did a first pass at this, which was incredibly impressive. It's called the mother of all demos. And if you type
Yeah, it's
ENGELBART
great.
into
It's basically
Google,
what the stuff we're using now, except it's still a higher level than what Alan Kay is talking about. Alan Kay is talking about doing this all the way down to the operating system. So we have these systems that we can are flexible for humans, all the human needs, without having to be these black boxes.
in the first page of hits, you'll find a reference to the movie of that demo. You should see what they were able to do back then on a tiny little machine.
Yeah, it's amazing. But they also took over hardware that it took another 30, 40 years to be distributed widely. So it was this scaling issue became a problem. Like one link was fine, but like trying to do 10,000 at once, they didn't have it yet. Now that's all I could do is inspire people with this demo, and it did this. And this demo did inspire lots of people.
And when Engelbart's name comes up, and even in his obituaries, the only thing I could really talk about was the mouse. And this really bugged Doug. He said the mouse is just a dial on a car radio. We invented a whole car.
Right, but people love hardware.
Won't look at it.
Right, because the actual implementation of what you actually did wasn't all that useful or great, or you may have had this like a demo in your mind, Doug, but you didn't bring it down to regular people how with it like an office use, and they tried to do a little bit of that, but it wasn't really. It was very academic level, still this academic a dream of what could be. But with given the hardware and the limitations in 1 year, it is pretty impressive actually for where they started with and what was available at the time. There was lots of idioms they had to work out. This whole chording thing with the keyboard over here was a little odd. But the mouse people made sense. Instead of like pointing at the screen, you're using this little puck to move a thing around. That people were blown away by that, and it was a great invention.
You can get an idea of this. There are about 70 papers on the website devoted to him talking about these deep ideas. As I mentioned previously, only about 30% of what Engelbart was talking about got taken up in computing today. So this is a big,
Yeah, there's
huge
still
area
lots of
that's got
stuff there.
fireflies everywhere. And these are just 3 of the 17 or 18 principal investigators that ARPA put together.
Yeah, we would need to have a new revolution, which is why it's still ahead of us. I hope to see parts of it that integrating some of the ideas that Alan Kay. We have to have a new operating system. That's just it, right? So that's the whole thing. Is there's gonna have to be some new hardware that's gonna be based on this type of these ideas, not just a general purpose computer.
So these are the kind of people. And if we talk about cooperation and methods, we've got to talk about the blind philosophers trying to figure out an elephant.
Yes.
This is a classic thing. And they all have this flaw that I mentioned in the beginning, that they think what's between their ears is not belief, but reality. So of course, this leads to war. And after thousands of years, the idea of compromise comes about. But
Right.
this does not lead to
Lots of death, lots of gnashing of teeth, lots of going back and forth, and all this baloney, and then we come to either a shared religion or a shared understanding or a realization that it's better to get along than to kill each other. This is like what the. How long did this take? It took in Europe. It was just constant, over and over and over and over and over again until we got to like at least like a Christianity where we could all agree at some point. And even then, in between, it's just been so bloody to get to compromise. And usually, it's just like after much sadness, sorrow, death, destruction, we always come back to okay, well, we could talk this out.
pretty picture of an elephant or a way to make an elephant. And in fact, this is my picture of the way computing is today. Practical computing is just a horrendous compromise.
Oh yeah.
Almost none of it was necessary.
Well, I mean,
now if you get scientific philosophers, they've learned how to cooperate.
Can define necessary. People had to explore the space with the stuff that they had, given where they were at, which was a lot of trade secrets, a lot of proprietary stuff. A lot of people wanting to be on top and be the one in charge, running the whole show, and didn't want to give anybody else the credit. They wanted to be the guy, wanted to be known forever, of all time, to be the one. It's like, and that's human. That's human. That's just humans doing human stuff. Come on, let's not get all excited about it. That's why we still have the computer revolution to look forward to.
Right? Science works by looking at parts of things and looking at what other people have looked at other parts of things, and other people looked at other parts of things, and
Right.
eventually coming to conclusions about the whole.
Right.
So that's a really good idea. But in fact, science, because our brains
But
want
it
to be
takes
right,
cooperation and a culture that values that, and the current one we're in right now doesn't really do that. Now, the stuff that generated that Alec K was talking about at that time, there was still a spark of that culture left, but it's gone now. So we're in this extractive style, warlike thing where everyone's got their little fiefdom, and I'm the best, and you're the way you suck, and hostile takeover and stock buyback.
rather than think, these can turn into something like a religion. And the reason we don't want to come up with blind belief there's always more.
Yeah.
There's always more, and what it is something that we can't imagine.
Yeah.
So when we give a name to something, we're hurting our belief.
Right.
In
But this is humans because we're living this physical world, and our language and our culture has been solid things for eons until we came up with computers and the math and science, which started with this more idea space. Like, how do you concrete ideas? Like, even the subatomic physicist guys had to make the little energy balls actually into particles. Can't get away from it. It's like our language is constraining us. It's making it very difficult to get around it. So we're gonna have to have a leap in the language.
because we've defined it
Human
as a
language. Good luck with that.
category now, we've hurt our ability to think more about it because it already has a set of properties. It already
Talking about English prime to be the things that are. It's like, no, this has the aspect. Everything has the aspect of the thing, but the thing is never actually the thing. What is the thing in itself? I don't know. God. What is the actual thing in itself? That's a good question, man. It's the network of connections around the thing that actually makes the thing, not the thing itself. Super hard to get through this when we have this quantum level reality like awareness. It's like there is nothing that is anything. It's just the connections of the thing and how it relates to other stuff. And it's totally subjective too.
is the thing that the word denotes. And here's an ad I suggested to Apple many years ago for the kind of people they wanted to have at Apple. What kind should they be? And I suggested, well, make a picture of something like this. The right hand has to be able to do with
Good luck in this culture, man. They just want to pass the leak code exam and make Apple change, right? They'll just leak code. This other side, forget it. No, no, this is noisy. This is messy. This hasn't. This can't be done on a schedule. We don't know when it's finished. We don't know when you're begun. We don't really know what this means, but we'll do this one over here. If you can leak code grind, and then you can be an Apple. So you can see the culture's changed quite a bit since Alan Kay, which is really sad because he remembers a time when this was the way. People did at Apple did act like this. I remember I was around people at that time doing that stuff, so it was a thing. But it's gone now, right? Stock buyback.
good P implies Q, and the left hand, the right brain, has to be able to do good woo woo.
Yeah. Yes.
And what is good woo woo? Because the thing to understand here, let me just take a second here.
It's all the intangible human shit that we all actually makes life worth living.
The thing to understand here is it was really hard to invent good P implies Q. It was only invented a few thousand years ago, but once we did it, it turned out to be fairly easy for us to do. And humans are more or less born.
Like the mathematical like categorization stuff. We can do a little logical representations and stuff, and it seemed to work quite well.
Babies are born with good woo woo.
But it's not the actual thing. It's just a representation of it.
And woo woo in general. And the problem is that most woo woo is actually quite dangerous for the human.
To the bureaucracy, yeah, it's super dangerous because they can't categorize it. and it frightens them because they don't have full control over it. Never will. I guess it's outside of the epistemological boundaries.
mind. So you have to find good woo-woo.
I
So
mean,
here's one definition.
good is context specific. Let's keep going.
Art is a lie that tells the truth.
Okay, I agree.
And learn the rules like a pro. That's the stuff you can do on the right-hand side of the board. So you can break them like an artist on the left-hand side of the board.
Fair enough.
You got to do both, or else you're just bullshitting around.
Yeah, agreed. Copying somebody else.
And this is hard to do in school because,
It's super. Yeah.
is the best thing ever invented to keep you from thinking about something important for more than a few minutes.
Minsky, yeah.
And you have to ask that about where you are
Nailed it.
right now. Even though I'm a professor there and Len is a professor, schools have their own way about them.
Mhm.
Like the fact that this talk actually has a designed end. Back at MIT, they would just get Marvin talking and he'd run out of steam in about 6 hours or so, and everybody was happy.
Yeah, that's kind of how that's how Zero was about. They would just go on, and there'd be curious people looking to try and do something interesting. And a lot of it didn't work. A lot of it was pointless. A lot of it's silly. All of it's like, ugh, poorly implemented. But they were making progress, exploring a space, and it was no container.
Here's another genius, huge influence on me. He said, institutional education seeks to make the strange familiar. Well, that sounds kind of reasonable.
The
Yeah,
woo.
that's what you're paying them for. Things you don't
Right.
understand, you want to now understand it. But
Correct. Yeah.
Jerry says the job of real education is to make the familiar strange again.
Yeah.
It's the stuff that
Oh yeah, Jerome Bruner gets it, man. Adventure driven. Let's go.
has come embedded into our belief system about normal that is keeping us being pedestrian. So he says, what kind of thinking would you do if normal could seem strange and not normal? You would have been able to escape your present. If you escape your present, don't forget to use a lifeline.
I mean,
how do we measure things?
Sometimes it's you get lost, and that's just the price you pay. The like finding back your back way back.
Well, usually with graphs that go from
The price for
the left
adventure.
in the past,
price for exploring
towards the future, going towards the right. And if something goes up, we say yay, and if it goes down, we say boo, and so on and so forth. Mm-hmm. And if you think about this, graphs like this are complete bullshit.
Yeah.
And the reason is, in order to understand whether we should say yay or
I mean, it's one aspect of it, but it's not the actual real thing. So let's keep going.
We have to have a threshold. And the threshold might be up here.
Okay.
Like these could be reading scores for children, and the children are never learning to read here. They're getting better or worse at what they're not being able to do. And so the key to make progress here is to understand that both better and perfect are the enemies of what is actually needed. Better is the tough one in engineering school because you get rewards for doing something better. Mm-hmm. But what we're looking for here is something new. And to get something new.
Yeah, there's refinement or there's exploring, right? There's very different ways of thinking about the problem. It's very different mindsets. And it takes different, very different risk levels because the refinement is you can measure when how far you are away and if you're getting closer or further away. When you're exploring, there's a pretty high likelihood that you're gonna find nothing, man. That you're off in the weeds, and you don't really know how far you are from the weeds or how close you are to the new thing. So risky. So risky, so prone to fail. But you are failure. Your name is failure. You are experiments that didn't go as expected. And you look foolish the whole time until, oh my God, you found it. How long? You're a genius. Overnight success is like, how long did it take? It took me about 20 years. It took me about 20 years to find that. Let's keep going.
So we have to come up with the minimal idea that is just above the threshold. It's just into the blue.
I mean, you hope. That's usually the edge you're working anyway.
Once we've stepped into the blue, we're actually in a different way of thinking about things. So this is, like going from not having mathematics to mathematics, or not going from not having writing to having writing.
Okay. Yeah, you get technology, you get a little, you discovered a thing that gives you another leap up, or your customer a leap up.
As to having science, these are big things.
You can.
So you want to look for that star, and the learning curve, you might have to start off below where other people think you should be.
Right. You have to go back to the basics, go to the fundamentals. Or in adventure, you have to go talk to the customer and actually talk to them, not to look at the surveys that all customers have already done. You have to go talk to see Penny. I don't just want to read a look at the studies online.
But the main thing is to get up there. Okay, so here's another example. World's greatest hockey player, made many, many more goals than anybody, and he was not a big guy. had a couple of nice sayings. You miss 100% of the shots you don't take.
Yes, this is the experiments you don't do, you don't get the information from. So all experiments, if you're having the mindset of science experimentation, that you're probably going to be wrong. This is the daring bet that all scientists who are working in a new field or trying to explore space are all dealing with. They're probably going to be wrong with all of it. That's why it's so heroic when somebody breaks through. It's because people that understand what's involved, if you're just like, whoa, you went all the way. Right. So experiments that aren't done, you don't get the information from. That's a great way of thinking about it.
People do that all the time. You don't try enough. And here's this big one. A good hockey player goes to where the puck is.
Right.
A great one goes to where the puck will be. And he didn't.
Okay. I don't like this quote because it implies you'll know where the puck is going to be. And unfortunately, with this exploratory phase, you're just guessing where the puck might be, and you're hoping your experiments go right. But you don't know, and you never will know. So it's kind of cheeky because it's like, oh, you have mystical powers. It's like, it's not quite. It's just like, after a while, if you hit the puck so many times, you're gonna like eventually have some stochastic, like bell curve thing about where things were gonna be, and you put your time and energy into thinking about doing that. When most people are like, what? I want to fight a guy on the ice. He just called me a name. He just called your mother a name. Let's go knock this guy out. And Wade's like, where's the fight gonna happen? And he's like paying attention to that kind of shit. It's like, okay, let's keep going.
Calculating the trajectory of the puck. He meant getting to a place where one of his teammates could pass him so he could do a quick shot on goal. That was the Wayne Gretzky game, and we could play it in technology. So here's an example from my own career. I had a woo-woo intuition about children having their own portable tablet computers in 1968, which was impossible back then. But the second stage is
it was possible to think about it. We had TV. We already had some rudimentary computers. You'd been playing with computers for a while. You know about the Visit Sutherland. You just knew, and you saw the miniaturization process happening. You knew that eventually it would come down to this. But so it was easy to imagine this, Alan. But the other stuff that you're imagining about the cellular stuff and having to use messages, and that's lets you have a scale up complexity. Nobody was talking about that. Nobody saw that. So that's the difference.
A favorable exponential, and there was one called Moore's Law. And this allows you to take this
later
intuition out 30 years. And out 30 years in the future, you could say, you can ask, would it be ridiculous if we didn't have this? And 30 years, that's 1995. The answer is, yeah, it'd be ridiculous if we didn't have tablet computers by 1995. Okay, so
yeah, so I mean, they happened a lot sooner than that. But by 68, they were already having the miniaturization process. So we saw that back then. And it was not mysterious to do that projection forward, that they'd have tablets around that you could be carrying around. And by what's 84, 85, they were doing luggables with or 86, they were doing luggables with Mac. And they had technology like that before that. So I mean, that's not the impressive part to me.
Bring the idea back to the mid 80s. Can we do something by the mid 80s? Yes.
Yeah.
But software takes a long, long time.
Right.
We're in 1972 now, so
well, the hardware took a long, long time. Sorry, the hardware to get to that point took a long, long time. Let's not kid ourselves. And the software hardware is just a software that's more solid. The gradation is not as thick as people would like it to be. The hardware is much more permanent, hard to change. It's solid and it's very difficult, and the software is supposed to be soft to change. But you have to design the software in such a way so it can get over the hump of just we have the thing where, oh my god, we can do this on a computer, versus how can we make this change and update it, extend it, make it understandable, make it debuggable, make it modifiable, make it monitorable, all that stuff that's cost so much money. That's the stuff that Alan Kay saw back then. He was like, okay, we have this to manage this level of complexity. You're gonna have to do cellular structures, which is, having everything goes through an API. You can't just punch your way through. Let's keep going.
What we need to do is to make a bunch of flexible supercomputer time machines, personal, make a lot of them, so the researchers can live and work in the future. That is what we did at Park. That $ says sort of Moore's Law means.
I mean, they put this thing together. They took some of these ideas and they put it into a machine. Definitely way too slow, but they were right on the cusp of it. They should have kept going with that. Xerxes could have dominated the whole planet if they went forward with that. So, but they didn't. So, but we have this other thing that was a cheap knockoff because this thing was still running the small talk stuff underneath, and all Jobs and Gates, when they saw the thing, they just saw the windows and like, oh, that's the important part. It's like, no, it was this other thing. That's just gooey stuff you're probably gonna get to anyway. That was not the important thing. It was this other stuff, man.
That
This highly modifiable, self-modifiable system that was completely customizable by you, changeable. Everything was changeable system.
that for most points in the future, you can have them now if you're willing to spend a lot more money.
Correct.
The commodity thing in the future is the supercomputer of the present. Build the right kind
Well,
of
at that
supercomputer in the
time,
present,
yes.
and you now have years to work on these really hard software ideas. And that is where the star was at Park. The dotted line there says you better do this really quickly, or else you're going to get submerged into tool building. You're going to be doing just computers and operating systems, and you're not going to be doing what you originally trying to do. So you have to.
Well, that was Alan Kay's fear at the time, that he wouldn't be able to get people to convince them to get to make hardware for this operating system like this. So the classic Unix style stuff just took off, and it was just that's became the desktop stuff and just miniaturized on that frozen in time idea set, which was happening at the same time as the Xerox Park stuff, but that Unix stuff took off before Alan Kay was able to show people that the software thing is the thing that's going to cause you problems, guys. And everyone's like, no, we got the hardware.
Have a lot of chops to do this. And in fact, the Alto was done in a period of about 3.5 months by an absolute
Amazing.
genius, Chuck Thacker.
Yeah, that's amazing.
And once you've got this, you can start inventing the software of the future. And the supercomputer nature of it means something like user interface.
Well, we usually mean the processor speed, but let's keep going.
You don't have to optimize. You can just do 10 experiments a day for a week. Throw away your code. Don't even bother stay, because you can put a higher level language on it. You can do experiments. You don't have to optimize. You need to find out how the users respond to things. And then on the right-hand side,
that was the small talk stuff he's talking about there.
If you're willing to optimize, you can do software like is going to exist in quantity in the 80s. That happens to be the first version of Microsoft Word, which was done at Xerox Park. It made Microsoft many, many billions of dollars when it was released 15 years later.
Yeah. Yeah, that's what they're doing. The WYSIWYG documents is what they're talking about there.
Right?
What he's talking about.
Okay, we're coming down to the end here. So 1963, Lick wrote a memo. Members and affiliates of the Intergalactic Computer Network. They asked him, why intergalactic? And he said, well, engineers always give you less than you're asking for. So I want a worldwide network. So
I love this story. It's great. I'll listen to it again.
Quit bitching and moaning and scale it down. It's still going to be worldwide. Got this great line here. If we succeed in making an intergalactic network, then our main problem will be learning to communicate with aliens.
So I really love this thing because it shows that the ARPA people were very interested in space and space travel. And honestly, this is kind of proof for me of a secret space program that had existed for a long time and it continues to exist. That we've had interstellar travel with humans for a long time, and much longer than anybody thinks. It's well before the 1920s. There's evidence of it, and this is just more evidence that ARPA was set up to initiate people into the galactic community. Have you not heard this before? Then here you go.
We'll look at that in a minute. And to this psychologist, he said, at this extreme, the problem is essentially the one discussed by science fiction writers. How do you get communication started among totally uncorrelated?
This is so funny. This is the beginning of the internet, by the way. I just want to point this out. Not being weird or anything, although I am. Look at this.
Sapient beings. And he thought here that scaling more or less destroys.
Dealing with sentient spacefaring races and trying to figure out a network that we can have a common language on.
Communication, even amongst humans. And scaling and technology is going to destroy communications and so forth. So this is what we need to think about.
Well, it means it's going to destroy the existing networks. Yes, the telephone networks were coming to an end at this point in time. They knew they were already reaching capacity. They were not. The switching load was going to have to be dealt with, and that's when they're doing. ARPANET was also involved with. It's like, oh, we'll just do this packet thing. Just digitize stuff, send it, and it can travel a bunch of different ways, scaled up, as opposed to do line to line, point to point, everything.
And he and Bob Taylor wrote a paper, of which I've expanded on a little bit. So the idea is, here's a human who's trying to say, I'm come in peace, and the alien is saying, maybe I should kill this guy.
Game theory.
Between two humans, a description of something with a mane and hooves and a tail can be a horse for one guy and a zebra for another.
Yeah.
Here's our multiple brains I talked about. One part of my brain wants chocolate, the other one realizes I should have an apple. Then we've got this new thing, the computer. What's on its mind? Not much. And
Not
it
at
doesn't
all.
understand what a horse is, that's for sure.
No, it has no idea of what that is.
So when we're talking with somebody else, we might not be able to get together on what a horse or a zebra is, but we have a better chance with a hamburger worldwide. So shared context is what we're looking for.
Okay. Yeah, sure.
And
So this is the whole word definition problem. We have to agree on the definitions of words and what they mean. And if you don't agree, there's no way to force people to agree. It has to be a voluntary thing. That's why this cooperation thing has to come along. You have to see the other person kind of as yourself, so you can treat them with ethically and honestly. But that comes from that warring period where we survived that. Let's keep going.
if we find a way, and what we do with language is to try and point into what we think is the shared context between us and the other person. So if we look back at the theater here, what is it? What is shared? What the theater is for is to reflect the intelligence of the audience back to them. You're not trying to teach them. I'm not trying to teach you right now. I'm trying to give you something that you can reflect your intelligence back on.
And that's why I love Alan Kay versus Uncle Bob and all these other guys, software developers, software conference guys, because this is the whole purpose of this. That's why there's not very technical, not much technical work here, not much technical talk, a little bit, but not much. But it's more about these ideas and concepts and how to think about your problem.
So the theater has to do most of the negotiations for the audience. That's too bad. But writing and reading are the same thing, same idea. And there's a huge difference between a good writer and a bad writer for these reasons.
Yes.
So let's think of communication as an extension of the gesture. So what could two different computers have in common? Well, it could be something like the dynamic messaging of real object-oriented programming.
Where she's talking about the real OOP, not the C++ stuff, but everything is behind an API. There's everything you have to call. You have to come through it. Everything has to go through an interface. Now the implementation side one, it doesn't matter. It doesn't really could be changed, whatever. But everything has to be through an API, through an interface, and that was Alan Kay's big idea. It wasn't objects. It wasn't classes. It wasn't hierarchies. It wasn't inheritance things. It's messages so that everything can be decoupled and asynchronous, and hide the complexity and behind a layer that's impenetrable. Keep going.
Could be something like what Linda did, but with David Galerner. You still have the problem of real aliens, but let's look at the problem with a person.
The real aliens. See, I know they know about this stuff, this real alien stuff. They're just so casually talking about it. It's like, okay, they could use a different thing, but let's keep going.
People and computer, what could they have in common? And so what can we make that is going to beam the audience's intelligence and knowledge back out to them? What should we put on the stage? And so the GUI is a representation of what the computer is thinking about.
Well, it's some designers' representation of what humans want to do with the computer, and then we're using the computer to represent what humans want to do. The computer is completely neutral. It's just a damn machine. It's just lights. It's just a bunch of switches, basically fancy damn switches. Now, what it represents, we overlay our meaning and our human meaning on top of these things. This is a Winnie the Pooh. This is a little gremlin. This is a word meaning simulation, meaning it refers to, but what's actually is just little switches on and off, right? So let's not get it twisted. I know what he's trying to say, but I'm very pedantic with this because this is humans designing it, right? There is no anthropological thing happening with the machine. It's humans imbuing their ideas and concepts that other humans are then responding to, reflecting upon, and then imbuing with their own humanness. Let's keep going.
In a form that humans can understand. The human can actually gesture at the topic that he wants to talk about. Each window holds a context and is a topic for conversation. All the possible conversation are active, no modes.
Right.
Undoing is critical everywhere. Gesturing and dragging engages the body brain. pictures are more memorable than words, so use those. Doing with images.
And this is how humans do it, but the computer don't give a fuck. They don't care. But humans care a lot about this.
Make symbols. And this is kind of Jerome Bruner 101. This one is particularly important. Okay?
Doing with images makes symbols. So we are symbol manipulators. We're tool manipulators because these thumbs, right? We've evolved to use tools, and we have physical objects. So we want to have symbolic objects in our minds, and then we use those to manipulate with our mind thumbs,
So this is kind of a
our mind fingers.
summary of the way people were thinking back then. And if you think about the part GUI, of all the things that this research community did back then,
It's the arguing.
the thing that made the trillion-dollar industries was
True.
not just Moore's law.
No.
Because there was nobody to.
No, this was not Moore's law. This is something else. This is the exploring the space and having license and encouragement and the culture to support people who are capable of doing these things as responsible adults that can communicate calmly and without having a pressure. It's like, oh, you didn't deliver to how many points on this sprint? I was 6 points. You did 4. You're fired. You're not a good performer. It's like, okay.
Sell Moore's law or even.
It was never going to come from that. Those are like refinement places they've already found the ideas. They're not worried about trying to explore an idea space. They want to refine what they want. If they can cut costs, they would. It's like that's a completely different than what he's talking about.
Reason to do Moore's
law. Where this stuff came from. It was all adventure driven. The stuff he's talking about is basically adventure driven, but it's very like had a culture of creating, culture of tinkering, culture of exploring, culture of like paranoia and war. And just getting over World War I and World War II, which were extremely bloody. Lots of people died. All these people had friends who died. Let's keep going.
Law at the scale it was done, unless millions and billions of people could actually use this stuff. And the reason millions and billions of people can use this stuff is because of the invention of the GUI.
Right. Correct. That is the only reason why this stuff can access, because I started using these computers before the GUI was a thing. All those command line stuff, and it was very nerdy. People were just like, what the hell is all this stuff? And it would take you many, many hours to understand how this stuff worked, and you had to be super interested, really want it for one reason or another, until the GUI came along, and that changed almost everything almost overnight. It took a while for people to accept it. The computer people who are doing the command line stuff, took them a while, but new users who you've never seen this before, like, oh wow, I can do that. That's totally revolutionized. That was like one of the first revolutions right there was a desktop. Please keep going.
So I don't even know what time it is, but
I'm going to do part 3 on this one. I'm having so much fun commenting along and filling in gaps for the old man. All right, give me a like and subscribe, and I'll talk to you soon. We'll probably finish up tomorrow, part 3.